Hello, I'm the awesome tutor, and today we're going to be looking at electromagnets, the motor effect, transformers, electromagnetic induction, all that stuff. So here we have some magnets. Now we know that like forces, they repel. But here we have north and south. They are unlike forces, and they're going to attract each other. And we know that the magnetic fields always flow from north to south. So here we have the flow of the magnetic field from north to south, always from positive to negative. Now, if there is no current in a wire, there is no way there's going to be a magnetic field created. But if there is a current in the wire, because here now you see the switch is closed, then a magnetic field will be created, okay, around the wire. This is all to do with electromagnetism, how electricity and magnetism are linked. And if we change the direction of the current, we change the direction of the magnetic field. So now it's going to go the other way. And this is how electromagnets in scrapyards work. They switch them on, they pick up the things, switch them off, they drop the things. How do we increase the strength of an electromagnet? Well, we put it in coils. If we coil it around, the strength of the magnetic field will be massively increased. And the more coils we have, the stronger the magnetic field. The current, if we increase the current, we increase the strength of the electromagnet. And here, if we put an iron rod inside the coils, the strength of the magnet is increased even further. But why iron? Because iron loses its magnetism, most of its magnetism, when the thing is switched off. If we use steel, its magnetism is still there after it's switched off. So if you switch something off and you're using a steel electromagnet, then it's essentially not going to be switched off, because it's going to keep attracting things to it. So that's not a really good electromagnet. That's why we use iron. Now, we know that a wire with a current produces a magnetic field. And magnets have their own, or create their own, magnetic field. So what if we put the two together? A wire with a current, which produces a magnetic field, and magnets, which have their own magnetic field. What will happen is, if we place the wire with the current placed in the magnetic field, this creates a force. Because the magnetic field of the wire and the magnetic field of the magnets, they interact. And therefore a force is created and the wire moves. The movement of the wire, this force created, is called the motor effect. And this all has to do with Fleming's left-hand rule, which we will talk about later. So how do we increase the size of the force? We either increase the magnetic field strength, so the strength of the magnets. We increase the current, which will increase the strength of the magnetic field of the wire. Or we increase the number of coils in the wire. But you should know that if the conductor, the wire, is placed parallel to the polarity of the magnet, there will be no force. So you're moving it along the magnetic field, there will be no force, because there is no magnetic flux. Magnetic flux means cutting through the magnetic field lines. So here's Fleming's left-hand rule. Force, field, and current. So you have to do this with your left hand. It won't work with your right hand. You put your thumb up, and then your index finger, your first finger, has to be perpendicular to it, at right angles to it, and then your middle finger at right angles to them. So it's like a y, x, and z axis. So here we have the thumb represents the force. So your thumb is the force. And that's going to be the direction of the force, whether it's going to be up, down, left, or right. Your first finger is going to be the field from north to south. How do you remember it's from north to south? North, the knuckle, then to south. The current is going to be your middle finger. From positive to negative. So how do you remember this? Well, thumb, movement, motion, so that's the force. First finger, field. Second finger, current. And you have to keep them at right angles to each other, otherwise it's not going to work. So let's look at some examples. Now I'm going to do the first one, and then try the other ones on your own. So let's put our left hand in position, force, field, current. Now, we want to know which direction the force is. We know the direction of the current, it's this way. We know the direction of the field, north to south, flip it over. Okay, current, north to south, and the force is pointing downwards, so the force is going to be down. Now try the other ones, pause the video, and then I'm going to go through them very quickly. Okay, current's going that way, and north to south, flip it over. Current, north to south, forces, again, downwards. Now current's going this way, it's north to south, forces, upwards. Okay, what about this one? The direction of the current, not the force. So here you have north to, you can't see my hand. North to south, okay? The direction of the force is going to be upwards, and north to south. The direction of the current is going to be that way, away from you. The polarity of the magnets, okay. Current's this way, force is downwards, so the polarity of the magnet is going to be north to south, like that. What about this one? The force is downwards, north to south, currents going away from you. And they do ask you questions like this in the exam, so it's good to have some practice. Let's move on. Okay, so what we have here is a loop of wire inside the magnetic field of the magnets. And there is a current going through the wire, so there's a magnetic field with that. And because of Fleming's left-hand rule and the motor effect, there's going to be a force on this wire going up, a force on this wire going down. Because the current is in opposite directions. So that's going to create a moment. And it's going to rotate rotate clockwise. But then when it gets to 90 degrees, the currents are still in the same position, but using Fleming's left-hand rule, north to south, currents that way, forces up, north to south, currents that way, forces down. It's not rotating anymore because the force is putting it up, putting it down. It's not going right or left. It's not making it move. So the wire does not rotate here. And we know that forces are different directions. So the forces are in different directions here and here. But here they can rotate. Here they're not rotating. So we can fix this. So we use split ring commutators to fix this, which I'll talk about later. So here, as I said, because there's no moment, it does not rotate. Okay, so here we have our split ring commutators, and we have the source of the current here. So the direction of the current, it never changes here. It's always that way, then this way. Here, this is what's going to be rotating. This is going to stay stationary, this is going to rotate. because the split ring commutators and the conducting brushes here, which allow the thing to move freely. So here we have a moment, because of opposite forces, because of opposite currents, it's going to rotate clockwise. Now when it gets to here, we see that the current is broken, because there's a gap here now that it has rotated. So the current is broken for a little bit, but the wire keeps rotating because of momentum. So there was enough force here to keep it rotating after the current was broken. But then when we get to here, now if we look at the previous example, if this rotated again, so if this whole thing rotated 180 degrees, the direction of the current will be in the opposite direction. So instead of going this way, it's going to come this way. Instead of going this way, it's going to go that way. If you rotate it 180 degrees, because you're rotating the whole thing. And that means the forces are going to flip as well. So it's going to rotate clockwise, then anti-clockwise, then clockwise, then anti-clockwise. So it's not going to be much of a motor, is it? So that's why we use split ring commutators, where only the loop of wire rotates, but the source of the current stays stationary. So when it rotates 180 degrees, the direction of the current is still the same as it was before it rotated. So it keeps rotating in the same direction. Okay, so electromagnetic induction. Now if we move a magnet in a coil of wire, a potential difference is induced. Induced basically means introduced. So we create a voltage which creates a current, because the magnetic field is moving through the conductor, which is the wire. So here the magnetic field, we're moving it back and forth, back and forth, back and forth in the coil of wire. So we're creating a force with a magnetic field, and that's what's going to create the potential difference. So if we move a magnetic field through a conductor, we create a potential difference. Here, we can do the same thing, but moving the wire in a magnet. So the conductor now is moving through the magnetic field, which also induces a potential difference. But we have to keep moving it, because if it's not moving, then there's going to be no potential difference. So we have to constantly move it. Now you should know that if we move this wire left to right along the magnetic field, no potential difference will be induced, because there's no magnetic flux, because the wire must cut the magnetic field lines, and this is called a magnetic flux, in order to induce a voltage. If we move it along the magnetic fields, it's not cutting through them, so the voltage is not induced. The potential difference is not induced. So it needs to move up and down. And here, this way, back and forth. Okay, transformers. So here we have the primary coil, the secondary coil, and an iron core. Now there is no way the current can pass from the primary coil to the secondary coil. Here we have the power supply, which is an AC current. It has to be AC, and I'll talk about that later. So AC produces an alternating magnetic field. So an alternating current produces an alternating magnetic field on the primary coil, because the primary coil, see, is attached to the AC current supply. And this magnetic field is transferred through the iron core. So here we have the magnetic field. And it's alternating, so it can go this way and it can go that way. It's transferred through the iron core, and the magnetic field interacts with the electrons in the secondary coil. And this induces a potential difference. So I'm going to go through that again. The alternating current produces an alternating magnetic field on the primary coil. This is transferred through the iron core, and the magnetic field interacts with the electrons in the secondary coil, which induces a potential difference. Now, questions which come up on transformers and electromagnetic induction, they are like 3 or 4 marks. So you need to learn the process of how they work, otherwise you're going to lose a lot of marks. Now, I said it has to be alternating current. Why not direct current? Because alternating current produces an alternating magnetic field, a changing magnetic field. A direct current, DC, produces a constant magnetic field which is not changing. And that's not going to induce a potential difference because we need, as I keep saying, a magnetic flux. Okay? With AC producing an alternating magnetic field, there is a magnetic flux, but not with DC. Now, the potential difference in the primary coil, in this case, is going to equal the potential difference in the secondary coil. Why? Because look at the number of turns. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And so, if the number of turns are the same, and if the transformer is 100% efficient, then the potential difference will be the same. So it's proportional to the ratio of turns in the primary coil to the secondary coil. And that's how step-up transformers and step-down transformers work, which we're going to look at now. So if we have more turns in the secondary coil, then the potential difference induced in the secondary coil will be greater, as shown here. So the primary coil, the secondary coil. There is more turns in the secondary coil, so the potential difference induced will be greater. Now, how many turns is the primary coil? 1, 2. Secondary coil, 1, 2, 3, 4. Because it's proportional to that ratio, in theory, if the transformer is 100% efficient, the potential difference induced in the secondary coil is going to be twice that of the primary coil, because it's 2 times 2 gets to 4. Well, we have a problem here. So power is voltage times current, right? But power remains the same. Okay? The conservation of power from the primary coil to the secondary coil. The power remains the same throughout. So if we increase the voltage, we have to decrease the current in order to keep the same power. And why do we want the current to be decreased? Well, here we have the national grid, and energy is transported over a long distance. And we have a lot of resistance in these wires, which creates a lot of heat, which obviously hinders the effectiveness of transporting and transferring the electricity. So high current means high resistance. So to transfer electricity efficiently, we have to have a low current. But to do that, we have to induce a high voltage, a high potential difference. So in this case now, there's less turns in the secondary coil than the primary coil, so the potential difference induced will be smaller. But as I said, power remains the same, so if we increase the potential difference, we increase the voltage, if we decrease the voltage, the current is going to increase because the power has to remain the same. Okay? If we decrease the voltage, the current has to increase to keep the same power. Now here we have the conservation of power. So the power in the first one is going to be the power in the second one. That means the voltage times the current in the primary coil is going to be equal to the voltage times the current in the secondary coil. So if the voltage in the secondary coil, the potential difference induced, is smaller, we have to increase the current in order to keep the same power. So that's how the conservation of power works. Now this equation is the really important one, because it's the one that the exam board loves to get you to use. the potential difference in the primary coil divided by the potential difference in the secondary coil is equal to the number of turns in the primary coil divided by the number of turns in the secondary coil. So let's look at an example question. So the primary coil has 300 turns and 150 volts of potential difference. The secondary coil has 150 turns. What's going to be the potential difference induced in the secondary coil? So we use this equation. What we want is a potential difference induced in the secondary coil. We want this value. We know all three of these values, so what we do is we rearrange the equation. And so, if we rearrange the equation, it's going to look like, you're going to get this. I know it looks a little bit tricky because it's a fraction of a fraction. So what you would do first is you would put this value into your calculator and then divide by it. So what we have here, let's put in the values. The potential difference induced in the secondary coil is going to be the potential difference in the primary coil, 150 volts, divided by the number of turns in the primary coil, 300, divided by the number of turns in the secondary coil, 150. So 300 divided by 150, you should know, is 2. So it's going to be 150 divided by 2, and 150 divided by 2 is going to give you 75 volts. So that's your answer. 75 volts is induced into the secondary coil. Now if you're good at maths, then you don't really need this rearrangement. You just use ratios. Because the ratio of turns from the primary coil to the secondary coil, it's 2 to 1. So to get from the primary coil to the secondary coil, you divide by 2. So to get from the primary coil, look at the potential difference now, to the secondary coil, we, again, divide by 2. And that's going to give us 75 volts. So to get from turns to turns, we find that out. We have to divide by 2 to get to the turns in the secondary coil. So we divide by 2 to get from the potential difference in the primary coil to the potential difference in the secondary coil. But if you're not good at maths, you're going to have to use this equation and rearrange it, which is a pain. Here's another question. Why don't you try it this time? Pause the video and have a go, and then I'll go through it quickly. So if you rearrange the equation, you will get this. You put in your values, you will get this. Put it into your calculator, you'll get 2,500 turns in the primary coil. So now let's move on. Switch mode transformers. Now switch mode transformers are the transformers you see in your mobile phone chargers. And they operate at a higher frequency than normal transformers, 50 kHz to 2000 kHz, to 200 kHz, sorry. And they're lighter and smaller, unlike a normal transformer, so you can carry them around. And they use very little power when switched on, when there is no device connected across its output terminals. So what that means is, it uses very little power when it is switched on, but there is no load on it. So if your device is fully charged, or there is no device connected to it, then there's going to be no power consumption. So it uses very little power when switched on, and has no load on it, unlike a normal transformer. And the switch mode transformer has a ferrite core, unlike a normal transformer which has an iron core, because it is lighter and can work at higher frequencies. Now here we just have how a mobile phone charger works. You don't really need to know this for your exam, but it's kind of interesting, you know. Here you have the mains input, 230 volts, 50 hertz, which you should know for your exam. And then it goes through a frequency converter, which obviously converts it to a higher frequency. And then you have your switch mode transformer. And then low voltage, which has been induced here. AC to DC converter. Because your phones only work on DC because of semiconductors and all that stuff. Now how do you get from AC current to DC current is the question. And what you do is you use a diode. Because that has a high resistance in one direction. So that's how you get from AC to DC. Yeah, this has been the Awesome Tutor. Bye.